thank you for coming in great numbers, but who's dedicated once for a year. I have to say, I appreciate you. I appreciate coming on time. It's pretty depressing to talk to an empty room, but I'll do my best. And as more people show up, I'll probably ramp up my enthusiasm as well. Today, I want to cover test coverage. This is the end of our incursion into testing, and we've spent a lot of time on testing. And I know that some of you think that may be too much time, but you should actually expect that in your professional lives, you will spend more time testing and writing tests and dealing with tests and maintaining tests than actually writing new features, because this is the nature of software development. It's the only way we know how to get software to work. And until we invent a different way, we'll be doing a lot of testing. But today is something that is not specifically how you write tests, but more how you analyze what tests have, how good your tests are, essentially. Okay? So far we looked at designing your code and organizing it for testability, make it more testable, writing tests, writing mocks, and so on. But we also know that there's no way you can test completely a piece of code, if it's any interesting. Okay? So then how do you decide when you've done enough testing? So the first part of the lecture, I will look at some very precise metrics for how much the tests have tested of your code, and then we'll talk about how to actually use those in real life. So the idea for test coverage, specifically structural test coverage, is that you want your tests to actually exercise as much of your code as possible. Because if your test suite has not touched a part of your code, then there might be bugs in there that your tests have no chance of uncovering. So you don't know that there are bugs or not, but at least you know that your tests are probably not complete enough. The question is, how do you define this notion of part of code that you haven't reached? The naive version of this is, if there's a function in your code that you haven't tested, that you haven't executed in your tests, then that's a problem. But that's too coarse-grained. We will want to go from function level down to statement level, and even beyond that, you will see, because just naively executing all of your statements once doesn't mean that you covered a big part of your application behavior. But the general idea is going to be the same for pretty much the whole lecture today. We're going to divide the program into some notion of elements of coarser or finer granularity. Then we're going to be counting how many of those elements get executed during testing. And you need to use a special tool for that. I will demo to you a couple of those tools. So as the tests run, the tool monitors the execution and counts how many of each of these elements are covered. And then at the very end, you compute this metric, which is a percentage, number of the elements executed during testing divided by the number of elements in the program. And if you get to 100%, then according to this definition of an element, you have 100% coverage. Okay? And most of what we'll be doing is looking at different kinds of elements. Any questions so far? No. Okay, so what kind of elements can you have? The most basic one is a statement. That leads us to statement coverage. How many statements in your program have you executed during testing? But you will see, we have to be a little bit more precise of how we define a statement. The one that it's the most powerful form of test coverage measure used in practice is condition coverage, which is also called decision coverage, branch coverage, and so on. But I do want to point out that while condition coverage is very commonly used, it's kind of the high end of what's used in practice, there are more sophisticated coverage measures, and one that we may get a chance to talk about is data flow coverage. It goes even beyond condition coverage. And I do want to point out what's beyond state of the practice, because people are still trying to find ways to bring these into the actual practice. But you'll see that there are some difficulties with these. And the idea is that as you become more and more sophisticated about how you define the elements of program behavior that you want to cover, it's harder and harder to get 100% coverage. You need more and more sophisticated tests to actually cover data flow coverage compared to condition coverage compared to statement coverage. So let me now, I know that not many of you have taken the 164 compilers class, so I want to introduce in one slide a very basic notion about how a compiler looks at the structure of your program. And in some sense, the code coverage looks in the same way. The code coverage, by the way, uses compiler-like techniques to actually do its work. So it's not surprising that it takes a similar view to your program. And the idea is that you take the program text, and after you parse it and you eliminate comments and white space and all that, you understand the structure of the control flow of this program. And so here we have a bunch of statements and the conditional. Some of the statements happen inside the conditional. So what the compiler does, it will group these statements into a so-called basic block. So a basic block is one or more statements that have no conditionals within. Okay, so this is a basic block. This is a sequence of two statements, a basic block with two statements. This is a basic block with just one statement. So is this one. And notice that even though these two statements occur next to each other in the program text, the compiler is smart enough to realize that there is some control flow going on in between them, meaning that specifically in this case, this first statement only gets executed if b is less or equal to 0, while this statement executes no matter what b is. Okay? So essentially, the compiler constructs a data structure that would be graphically shown as this flowchart here. So the basic nodes are these kind of rectangular nodes that can contain multiple elements. There are these conditional nodes that have more than one outgoing edge. Most conditionals have two outgoing edges, but if you have conditionals with complicated and or, there might be multiple outgoing edges as well. And switch statements, again, have n multiple cases, right? Okay. So essentially, the control flow graph is this data structure that the code coverage tool uses and the compiler uses. And it's a graph, as the name says, and there are nodes and edges. The nodes are the basic blocks, sequences of statements without internal control flow, without internal conditionals. And the edges are connecting, essentially, notice they're directed edges, and they tell you how the control flows from one node to the other. Compilers and interpreters have these data structures internally. Is this clear? Okay, good. So we're going to be defining the first couple of coverage metrics based on this kind of graphs. But let's try to actually build the control flow graph for this little program or function in there. So this is how it shows in the code, okay? But some of these constructs, like the for constructs, has multiple elements. Has an initializer, j equals 0. Has a loop condition, j less than 2. Has a post increment operation, okay? So when the compiler parses that, it constructs an internal representation of how the control flow goes. And it doesn't have special nodes for for loop. All you have is branches and then go-tos, which are these arrows that go. So how would you describe this in the body of this method as a control flow graph? What would be the first node? What's the first thing that happens in the method? J is 0. Okay? So j is 0. And that's a basic block by itself, because there's no other statement that happens along with j equals 0 always. Okay? After j equals 0, what do we have?
If j is less than 2.
Right, we have one of these conditional blocks, which is a diamond or a triangle. And there's an edge here So if j is less than 2, so the true branch, what happens?
Checks for equality with x.
X equals j. Again, another diamond. And if this is true, then there's the print. Again, and typically you have these bodies of conditions have multiple statements, so they have still one node in the graph, but with multiple elements. Okay, so what do I do after print?
You go back to j.
Merge
Merge it with the false branch of x equals.
Right. So both of you are right. I do go to the j plus plus, but first I have to merge it. Okay. So this kind of merge in the graph. Let me just put here the j plus plus. Okay, and this is very common of conditionals. You have this kind of diamond structure, and then
You send it back to the diamond. J is smaller than 2.
yes, I do. Go back here, and then what? One thing is missing.
The false case.
4.
J is smaller. Yeah.
Yeah, this one. And this actually takes us out of the for loop, and we have x plus plus. Right? Okay. So it's important to, you won't have to draw this, but mentally you'll have to understand, because this is what the code coverage tool works on. And the code coverage tool will see each of these as an independent, if you want, statement. These conditionals, the prints, even though they may be written on the same line.
Generally, there's only one way to draw this, or there's like multiple ways you can write it.
There's typically just one way, but of course I could have arranged this graph on the board differently, but the same nodes, the same edges.
But when it becomes more complex, it's still there's only one way that is right.
Okay. It's hard to answer your question precisely. The same logical program can be represented as multiple graphs. For example, and this is what the optimizer does. Okay, there are some statements here that the optimizer may discover that are not necessary, or they could be simplified, and then it would massage this graph in something equivalent. Okay, but if you don't think about optimizations, about program transformations, then typically it's a fairly straightforward mapping from the text to the, and this the compiler does very early on, and it's called the parsing. When it does parsing, it does this. Then the optimizer comes and starts to make changes to these individual statements, or even to the structure of the graph. Okay, so this is, it should be the same graph, except it's perhaps arranged differently. Okay, so now that we understand what these basic blocks are, what these conditions are, and each condition has 2 or more outgoing edges, we can start to actually define the 2 structural coverage criteria that we'll be using. And one is statement coverage, or node coverage in this graph, and the other is all condition coverage. Okay, so but I'm going to be using this this graph, which is also, there's a conditional at the top, and there's a loop with it looks like a while loop with a D being the termination condition and E being the body, and then F. Okay, so on this graph you can define multiple structural coverage criteria. One is all condition coverage. All condition coverage means that if you run all of your tests and you keep track of which of these edges have been executed in each test, then you want for every condition to have executed both of the outcomes. So there must be at least a test that comes from A and A is false, and another test that makes A true. Okay? So, but notice that if you all you care is about covering all the statements, all the nodes, then you could go from A to B to C in one test. A to B to C to D to E, back to D and to F. So that's kind of the shortest test that walks through all of the nodes. And sometimes it's good to have smaller tests because when they fail, they're easier to debug. So this is actually not far-fetched for trying to think of, okay, how can I in one test cover as many cases? But I do want to point out that if all you care about is statement coverage, that this one test can get you 100% coverage in terms of the nodes. But you probably, or most likely, have missed, you don't have 100% condition coverage because this test has not executed this edge from A to C. You found a way to kind of go A, B, C. Okay? So you could argue that for this kind of code structure, there's no way you can have all condition coverage, meaning all of these outcomes of all of the edges in one test. Because one test has to either go through here or to there. It cannot do both in one test. So you need at least two tests for this. Any questions? Yes.
So you say it's written edge AC is required by all condition. What exactly it means? I'm not sure.
I will talk some more about this. So the only nodes that have more than one outgoing edge are the condition nodes, either switch statements or if statements. Okay. So all condition coverage means that throughout your test suite, you have touched all of the outgoing edges of all of the nodes. So if A is a condition, to cover the A as a condition means that you have covered the true outcome and the false outcome. Okay? If you want to think in terms of graphs, you can talk about edge coverage. It's kind of the same, except that while graphs may be useful for visualizing what happens, most of the tools actually present the outcome of the coverage in terms of the source code. So it's more like in terms of the conditions in the source code. So I'll talk some more about statement coverage and condition coverage, but I do want to kind of look a little bit forward, and you can go beyond this, covering nodes and covering edges. There's notion of loop coverage. So, for example, here you have a loop body, and you may want to cover this loop with 0 iterations, because you want to make sure that your loop works properly when you don't get into the loop. Essentially, valid D is false, you skip over the loop. You want to make sure that if you do the loop iteration once, so D, E, D, F, that works, and you want to try multiple iterations as well, because it's possible that in multiple iterations a bug will show up that is perhaps not visible in the first iteration. Okay? So as we go to more and more complex coverage criteria, they become a little bit harder to see, harder to think of the examples when exactly this coverage criteria would find the bug when simpler coverage criteria would not. But that's because they're more complicated. Okay, so for statement coverage, let me try to summarize it. Simply, you define some notion of a statement in a program, and you can do that. Every tool does that in some way, which may be a little bit different from tool to tool. If you have the control flow graph, then you may say that every node in the graph is a statement, but typically tools will actually highlight the statements in your source program. Okay, so let's. I want to show an example of how we actually compute statement coverage, and for this example, we will see that statement coverage, even though it's 100% for a particular program, doesn't mean you found all the bugs. So we'll use this program for a couple of slides, or more than a couple. For a couple of examples. So what this program does, it reads two inputs, X and Y, and it has, this is the interesting part of the program, the statements 5, 6, 7. If X is not 0, it adds 10 to X. If X is 0, it leaves it alone. And then it divides Y by X. and it puts the result in y and outputs x and y. So one way to draw the control flow graph for this program is as shown here. I copied this image from a textbook. It's not exactly how I would have drawn it, but it's the same spirit. For example, I would have drawn explicitly the node 5 as the node where the branching happens, but they do just 3 and 4. But anyway, the program has this kind of branch here in the middle. Okay? So if you want to do test coverage, you want to have one test which is defined in terms of some values for x and y that you pass to this program that covers all of the statements. And as long as x is not 0, it will make the program go from 4 to 6 and then to 7, obviously. And that, in one test, it can cover all of the statements. So if you put x equals 20 and y equals 30, so if x is 20, then x becomes 30 after this line. So when you divide, y becomes 1. Okay? And visually, this kind of red line shows you how the program executes. And this gives you 100% statement coverage. So in some way, if you're just very narrowly focused on getting coverage to be as high as possible, and with as few tests as possible, this is what you choose, or something like this, with x is not 0, right? Because in one test, you're done, if that's your definition of done. However, let's look a little bit at this program, what it does, and where may there be a bug in this program? Can you spot the bug in this program? If x is 0, what happens?
Divide by 0.
If x is 0, you bypass this, you jump from 5 to 7, and you divide by 0. And that's probably not a good outcome. So in some way, if you picked an input with x is 0, it would come 3, 4, 7, 8, 9. It would not give you 100% statement coverage. But in some way, it's a better input if your goal is to find bugs. Okay? So one thing that I want you to keep straight is I teach you coverage criteria. And those are used in practice, but don't take them as the actual goal. The goal is to find bugs. Statement coverage and other coverage measures kind of give you a hint of when you might be done. But there's no precise mathematical relationship between a higher coverage and more bugs found. Sometimes, as you can see here, lower coverage would actually get you to the bug. So one thing that people have done is to actually think of more sophisticated coverage criteria. So statement coverage is the simplest one, and clearly having 100% statement coverage can hide even fairly obvious bugs. So this kind of leads to a drive towards more and more sophisticated coverage criteria. Just to summarize some facts about statement coverage, it's the simplest coverage to measure. Any coverage tool out there for any language will give you statement coverage, and perhaps more. So that's why this is the first thing that managers would sometimes look at if they want to answer the question, do we have enough tests? Now, how big are these numbers? Microsoft, this is from some time back, they reported 80 to 90% statement coverage on their software when they ship. So now make your judgment. Is this high? Is this low? So let's say Windows, 30 million lines of code, 90% statement coverage. What does it mean? How many lines of code have never been executed?
300K.
35 million lines of code?
35. Just like 3 million.
3 million lines of code. They shipped code with 3 million lines not executed. So 90% looks big, right? But
relative.
It's relative. Well, it is by definition relative. There are some rules. Yes.
If like the percentage of coverage isn't necessarily correlated with finding all the bugs, why is the coverage number like the main motivator for managers?
Okay, so the question is why is the coverage number the main motivator for managers and such? I didn't try to claim that. In fact, the whole theme of this lecture is, yes, use statement coverage, but be careful. Don't make that your goal. So smart managers will not do that.
So what's a good goal then in terms of?
Well, the goal cannot be solely in terms of this number. There are other things to look at. And we'll kind of touch this several times this lecture. But I do want to point out that there are some rules that the government has put in place for very specific domains, like a medical domain for when the software is controlling a device that could damage health, for safety critical systems like nuclear reactor control systems or airplane or car control systems. And I'm not talking about the entertainment system, I'm talking about the stuff that can actually do bad things. And there they actually impose 100% statement coverage among many other things to kind of help get the quality up. But it's important to realize this cannot be the goal, or even if it's at 100%, it cannot be the sole criteria by which you decide to stop testing.
You mentioned earlier that test coverage is often not correlated with like how good the input is at finding a bug. Is there a formula to quantify like how like the coverage of your inputs, like like to quantify like if you've covered all your edge cases?
Well, so the coverage is the way to try to quantify how good your inputs are covering. Keep in mind, I've only shown you one way of computing coverage, statement coverage, which is the most naive one. We'll be looking at more sophisticated ones that are more precise. Okay? There's nothing that is, testing is not a purely mathematical property. One thing I want to point out is that 95% can be quite hard to accomplish in a big project. However, in my experience, if you do test-driven development, you will get to 90 plus without even measuring coverage, just naturally. Because you are thinking about testing and you are writing tests as you write the code. When you have a complicated situation, because you have done test-driven development, it's very easy for you to reproduce that situation with a new test that will actually drive your debugging and refinement and writing of that piece of code. So this will very naturally bring you to over 90% code coverage. You may still want to then fire up a code coverage tool to see what exactly is the number. Is it 91 or 95? And that might even point you to places that maybe you missed. Okay? So projects that have only 80% test coverage, almost certainly they haven't done test-driven development. Because if you start writing tests after the fact, you may even forget about some corner cases that you wrote 3 months ago. And those you're not going to cover. So let's look at, I want to build up on this example of statement coverage, motivate the next better coverage measure beyond statement coverage. Okay, so this was the test that we've done so far. And if our goal was statement coverage, we would say that we're done. But we know that we are not done because of this this fault that we have in line 7, which is exercised when x equals 0. Okay? So then people have asked the question, okay, if this is a situation where I have a fault here, but the fault only shows up if I'm coming from 4 directly, as opposed to if I'm coming from 6, then clearly statement coverage is not enough. What do I need? What kind of coverage I need? And that kind of led people to the idea of edge coverage. It's not important to just execute every statement. The context in which the statements are executed is just as important sometimes. And this statement behaves differently if you're coming from 6 or if you're coming from 4. Okay? So that leads us to condition coverage. which is, again, very commonly used in practice as a supplement on top of statement coverage. So the idea is that now, instead of counting how many statements, we're counting for every branch how many of its outcomes is exercised or edges. Okay, but keep in mind that the branch typically has two conditions, two outcomes. A switch statements has several conditions, and what you're computing is number of executed conditions divided by the number of conditions in the program. Now, while statement coverage is typically more easily understood, condition coverage is not as clear, and different tools define it slightly differently. In fact, they use different names sometimes for it. Sometimes you'll notice that the tool calls it branch coverage. But keep in mind that when they say that you have 100% branch coverage, it means that for all of the branches, both of the outcomes. So to cover a branch, you need to cover the two outcomes for it. Because of this, this is sometimes called multiple condition coverage, and I'm abbreviating as condition coverage. Okay. So coming back to our example, condition coverage will force you to make sure that for branch 4, you have at least an execution that goes from 4 to 6 and an execution that goes from 4 to 7. So you need at least 2 tests. And that, in this particular example, forces you to pick x equals 0, and which makes you hit the divide by 0 problem. Okay? So the example is chosen on purpose here to show that statement coverage is not enough and condition coverage finds the bug. Okay? As you might expect, even condition coverage is not perfect. Even when you have all condition coverage, you probably found more bugs than with just statement coverage, but not all bugs. So let me show you now a couple of examples of tools that do coverage. And there are many. Every language has at least one. Every serious language has at least one. I have worked with languages that are not mature enough to have these tools in place, and it's a big thing. But that's not the case for most common languages. So this output here is from a tool from the C language world. The tool is called Lcov, and it comes with the GCC compiler. It's essentially a counterpart to GCC. And this is actually fairly common. Coverage tools use some of the same tricks that compilers use. So they depend very much on the compiler. They are sometimes shipped with the compiler as an option. So GCC has built-in machinery for computing coverage, and you have to pass a special flag to GCC when it compiles your program. And then when your program runs, in addition to doing what it's supposed to do, it will emit a few files with data, with counts specifically of how many times different parts of the code have been executed. And then there's a separate program that takes that data, which is kind of raw numbers, and produces some visual representation of coverage, typically superimposed on source code. And Lcov is this. So let me try to explain what's shown here. So first, there's this insert, which I kind of copy and pasted from the screen of part of the output. This is a summary, and it does count line coverage, which is kind of stand-in for statement coverage. However, keep in mind, you can have multiple statements in a line, but it's about the same kind of thing. Function coverage, how many functions ever got executed? And how many times, how many lines were hit, how many total lines in your program. And then this is simply the division of hit over total. And then for branches, as I said, there are 4 branches and 4 have been hit. And keep in mind, for a branch to be hit, it means that both outcomes have at some point been executed. Okay, so that's the summary. If it's at 100%, that's in some sense, okay, you've exhausted how much you can get out of this kind of coverage criteria. But typically, it's never at 100%. It may be at 90% or 95%. So what becomes important is, where is the other 5%? What you haven't covered. And that's what you get in this view here. So This is the source code of the program here on the right, and there's two more columns. In this column, this is called line data. You probably can't see the heading there. These are counts. This is number 3, and this is 67,548. This is how many times this line got executed. Okay, and so notice that. Actually, let me try. I think I have a zoom in here. You can probably see that. Okay, so this is the line counts, and this is the branch coverage. Okay, the way you read this, and this varies from tool to tool. You have to learn the tool. This means there's a branch on this line, and it's this for termination condition, and it puts a plus on the true outcome and false outcome. For every branch, you want to see both outcomes. So this counts as a branch that's been covered. This is a second branch that's been covered. This is a conditional in the middle of the for loop. There's actually a lot of information here if you stare at this for a little bit. How many times do you think this function, okay, this is the whole body of the function. There's a for loop and there's a conditional inside. How many times this function got executed, got invoked? 3 times. Because every time the function is invoked, this statement gets executed. Okay? How many times the function returned? 2. So what happened to the third invocation?
There's an exit there.
Yeah. Okay. There's an exit here. But it could have been an exception in a language with exceptions. Okay. So this loop got executed 67,000 times, blah blah blah, but this one was executed 1 fewer times than this. So you can already start to picture what your test did to your function. And typically, what you will see, let's say this is a common case here. This is an error case. Something bad happened in the middle of the loop. The program aborts. Those are typically hard to cover. Those are typically not what you would think of covering when you write the first test. So if you didn't get here, the picture will look different. This will be zeros. And because they are zeros, this display would show them in red. Okay? So you immediately spot, okay, these are lines that are not covered. This will be red because you will see that this conditional, it only ever was evaluated to false. It never got into the conditional. So the branch coverage would go down. And you'd probably see that the function was evoked 3 times and was returned 3 times because you didn't have this. So you look at it and say, if I want to increase my coverage measures, whether statement coverage or branch coverage, this is where I have to work. I need to construct a test case that somehow ends up here. Now, this is easier said than done, often because your test cases have to give inputs to the program, and it's not always easy to construct inputs that hit your error cases. So, can you think of some error cases that are hard to hit? Error cases that you want to write in your code to handle, but they are hard to exercise in your test.
Say you have a function foo that calls bar, and both foo and bar would validate the input, so that when foo validates the input and feeds it into bar, and the bar may be some private method that you can't touch.
Okay. Yeah. So I think yes, that's actually it's a good example. You have foo does a conditional here if to check the input, and then calls bar. Say if input is greater than 0, and bar, because it's written defensively, it will also check the input. Right? So if all you can ever execute is foo, there's no way to pass an invalid input to bar. So you're going to see that this conditional is not covered because it's always execute equals 0, and it's not easy to actually make your program. So what you probably have to, well, you have to consider, does bar need to validate input? Because if it's only ever being called like this, maybe this is unnecessary. So maybe you have too much code that you're trying to cover. Okay, other examples.
You're dealing with like an external resource like server.
Yes.
You can't force it to give you errors.
Right. Let's say your application uses Google Maps API, and you do want to write code for what happens when Google Maps doesn't want to give you a map. Maybe you run out of quota or the network is down. That's hard to actually reproduce. So what do? I want more people. Come on, you should know this. What do? You create a mock. And with a mock, you can simulate the scenarios, even though they are harder to actually reproduce in practice. Others are hard to test scenarios. You run out of disk. You're trying to write the file write the boards. Okay? You're disconnected from the network and you're trying to make a connection. You think about it. In C programs, you run out of memory. Malloc returns null. Okay? Solid programs have those conditionals, and those will probably show up as not covered. So when your coverage is 90%, it's not because you haven't ran these 3 million lines of code that sits in a directory. That's never the case. It's 3 million individual exit statements for out-of-memory errors, which you put in there because you did a good job. It's just that you have no tests, so you just hope they work. Let's take a break now. I want to take a couple of minutes to show you some code coverage as I use it. Okay, so what I have here is this bond project. We have tests for bond. So bond is a testing tool, but we write tests for it because otherwise we can't get it right. And I am using, for Python, I'm using PyCharm, the IDE PyCharm, which has a sibling for Ruby. It's called RubyMine, and has a sibling for Java called IntelliJ. And I've used IDEs for many years, and these IDEs are absolutely great. And they are free for you as students. And there's absolutely no excuse not to use it, okay? And I know some of you prefer Vim or Sublime as a text editor because, I don't know, it looks more professional. But the argument would be, what if I asked you to write your whole semester project in Bash because it's more professional that way? That's really what you're missing if you don't use IDEs. So not only you get this coloring and all that stuff that other editors can do it, but this IDE is really integrated with a lot of things. So for example, this is a test, reconcile, accept, no save. I right click on it and I get all this menu. Remember the refactoring that we used, but here you can run it in the debugger or I can run it with coverage. So I am running this test only with coverage. I just click on that. It runs the test. It finished the test, and now, yes, it takes a second to think about it, and it presents me this coverage. It takes all the directories in my project. This is a PyBond for Python Ruby bond, and as you can expect, I've run one Python test, so it shows 0 coverage for bond. For PyBond, it shows that I covered 43% of the file, 61% of the lines with one test. Well, bond is not very big. And if you go in the bond directory and the actual bond.py, well, actually, let's look at bond reconcile. So I'm going to close this window. I don't know if you can see on the left edge these colors.
No.
Not at all, yeah. Okay, let me, you'll just have to believe me. There's a little pink thing here, and these are all green.
There's
Okay.
different things that you can put in.
Yeah, maybe for next time I can change the colors. But even this actually column is very. The point is that this tool has run the test while monitoring what line gets touched, and then it presents to you the result by essentially highlighting the lines that are not touched. So this line was not touched. Now, if you understand what the code is, this is the code that does the bond reconcile. And this is only invoked if you don't have a reference file saved the first time you run the test. And because I just rerun a test that I had before, it's expected I never got there. Okay? And it shows that 45% of the lines are covered. That's pretty good for one test. Now I go back to this window here, test results. And now I want to run all the tests for reconciliation. I say I right click here on the whole test class, and I want to run them all with test coverage. And then it pops up this window. Essentially, what happens is every time it runs test, it does this accounting of how much you've touched, and then it asks you, I have new coverage results. Do you want me to accumulate to the previous ones, or you want to view just these ones? Because typically, you want to either see the coverage for one particular test, just to have an idea of what this test does in your program, but sometimes you want to see the accumulated coverage of all of the tests. So I'm going to accumulate it. So add to the active suite. And now let's try to view what's tools, show coverage data. Oh, sorry, this is a different project. So now, okay, I'm not sure what happened. So what I wanted to show you that I didn't quite manage was that you keep running multiple tests, and then it keeps making more and more lines green, essentially that they were covered. And one thing you want to look at is when you run all of the tests, what's left, what's still not covered. And really, I don't know how good programmers you are, but for me, if I write 100 lines of code, I have bugs. And typically, they are in the trickier parts of the code. And those tend to be the parts that are not covered by tests. Because if they're covered by tests, they would explode. I would see them. So it's a very good thing to do. I hope sooner or later I'm going to convince most of you to use IDEs. Okay, now let's move along here. This is another coverage tool that I have a couple of screenshots on. This is the coverage tool by Atlassian. Atlassian is a company that builds software engineering tools. And we at Conviva, we use quite a few of their tools. We use their Jira bug tracking system. These are commercial tools. They're not free to use, but they are really very good. And this is their code coverage tools. They have a continuous integration tool that does automated testing for your code, and they have a Confluence. It's a document kind of sharing tool where we write comments and design reviews. So you probably can't read from the room all of the details in the slide, but I'll just point out what this dashboard kind of shows. So this is the coverage. So the tool name is called Clover, and it's the coverage for Clover itself. So when they wrote Clover, they wrote tests for Clover. And this shows how well these tests cover Clover. Up here, there are a bunch of statistics, like how many statements, 8,000 statements, 3,000 branches, 2,500 methods, 400 classes, 45,000 lines of code, and statements per method, 3.25 statements per method. This is one thing I don't like about Java. It just forces you to write so many small methods, very small methods. This shows, okay, so here test results, 786 tests in 13 seconds. This is actually very good. Imagine how fast these tests have to be to finish them all in 13 seconds. So this is something you can do in a stretch break. Okay, you spend the time 1 hour writing code. You let the test run. Kind of tells you if you've gone back, if it's worse or better than before. This kind of gives you a high-level view of coverage. You have 62% coverage in this case, and this shows you the distribution of classes, number of classes by coverage. So this you have about 100 classes with 0% coverage, and you have about 80 classes with 100% coverage, and then some classes with just 50% coverage. This is actually a fairly common picture. Can somebody think of why you may have such a high, spike here on 0% coverage?
Abstract classes.
Abstract classes. I guess that's a possibility. I was thinking of something else. So an abstract class is a class that never gets instantiated, but then maybe they shouldn't count those lines as executable lines either. But what else could be here? Let's say some of these have actual code, increments and conditionals and such. Nobody?
Say something like the Dropbox API we discussed before, like the delegate that you write for some other heavy loaded stuff, but you write mocks for them in the test.
Okay, so I think what you're saying is maybe you have some classes that you have mocked out in tests. So the class itself doesn't run. But then still, you should have some code for the classes that you're mocked. The Dropbox API is different because that sits on the Dropbox side. We don't care to cover that. This is code in our
No, I mean the delegate class.
Yeah, but this is still our code that I think we should cover. So I think my explanation for this is that these are probably classes or methods that are not used. Imagine that you have libraries in your code that are not used in Clover. Because generally, libraries are generally useful for multiple projects, but no single project uses the entire library. This can happen even more with methods. Okay? A class has many methods, again, because it could be used in many contexts, but not all methods are used in all projects. And sometimes you simply have that code that was inherited, it's a leftover from a previous iteration, and there's no way execution could get there. So sometimes looking at the 0% covered elements may point to code that you should delete. Okay, next, these two panels try to show some correlation between coverage and complexity. There are notions of code complexity that we haven't really covered in this class, but naively you could think of how big the method is. That's a measure of complexity. There are more sophisticated ones that kind of try to weigh more loops and conditionals than statements, just plain statements. So in this graph, on the x-axis we have coverage, 100% coverage is here. And here is complexity. So this corner on the lower left is methods with 0% coverage, not tested, but very simple, one-liner maybe, or empty methods, who knows, okay? Up here, this upper right corner, we have code that's very complicated. This is a method that's very complicated, but it's also pretty well tested, almost 100%. Okay. What you don't, which of these corners do you think it's the worst corner to be in? 4 corners.
Upper left.
Why upper left?
So complex and you don't test it.
Yeah. So this would be really bad here. You have code that has high complexity but very low coverage. Okay. So being here or here, it's okay. So generally under, if you want to compromise under the axis. So maybe the next one to hit with the test would be this. Now, without understanding better what this code does, it may tell you, okay, this is kind of complex and very low coverage. So maybe go and write some tests for this. But don't try to be the manager that makes the entire decision based on just this diagram, because you need to look inside what's in there. This is a different view of the same kind of data. Here, color means coverage. Red, bad coverage. Green, good coverage. Size means complexity. Okay, so this is something that's highly complex but covered. Okay, so the worst, you don't want to see big red spots in here, because big means complex, red means not covered. Okay, and then more views. I mean, it kind of ranks the methods, least tested methods, most complex packages, and then with a coverage percentage. And this is another kind of zooming in into the package. So probably here is somewhere where you may want to look at do either more testing or investigate. Maybe these are not used. So maybe they don't even deserve to be in the picture. Okay. Any questions? So you should learn how to use your coverage tools. If you use the IDEs, both PyCharm and RubyMine come with the built-in coverage. Very easy to use, just one click, and then just read and look at the output. And then there are the tools that try to give you more sophisticated output. Okay, I have another one here. This is from, it's also an output from Clover, the same tool. And this time it's testing the Google Juice project. Remember what Juice does a couple lectures ago?
You can instantiate stuff.
Yeah, it's a dependency injection library that's used to instantiate objects. Okay, and they wrote tests for Juice, and they put the test on Atlassian, and this is one of the UIs. And what I want to show here is, again, the red coloring for stuff that's not executed. This entire method is not executed. Okay, is that bad? Well, maybe the method is not actually used. Maybe somebody wrote it for completeness in this class, but it's not actually needed in the rest of the project. So it's okay for it to be 0, perhaps. But this is something interesting here. If you can see, I see that these two lines are red. It's a conditional line that was executed 94 times. So why do you think it's red? It was executed.
It's an exception.
No, this line, if entry equals null.
Because it always evaluated true during the test.
It always evaluated to false. So it never got into the test. And then you can see clearly that this is a 0, so it never got here. This line is red because statement coverage is 0 for it. This line is red because branch coverage or condition coverage is not met. Okay? So clearly, what do you do here? You can just say, oh, I want 100% test coverage, and maybe if that's your contractual obligation, you go and write a test for this. Or maybe you say, okay, I know this is not tested. Maybe it's enough to do a code review. Just look, make sure it's correct, and then move on. That's perfectly fine too. In some way, you have to kind of scan these things and prioritize. You have a limited budget for spending on testing. Okay, where do you go next? If I see a complicated set of conditionals and loops all red, I'm worried, because that is likely I'm going to get wrong. This probably it's okay. The other thing that I want to show, and this is very cool and very important, this tool can allow you to click on a line. So I clicked on line 649, and I want to say, tell me which tests executed this line. Okay, and then it pops up this window with the names of the tests, and I can click on the test and takes me to the actual code for the test. It also shows me of the 94 hits of this line, what's the distribution of the contribution? How many? Because maybe one test did all the 94 hits. Okay. Why do you think this is so cool, so important? how would you use this information? So let me tell you how I use it. Sometimes over the life of a project, I have too many tests because everybody keeps adding tests, and sometimes we have 10 tests that test the same thing. So it's good to know what is the relative contribution of each test in terms of coverage. Because you may discover that some tests are truly deserve to be deleted because we now have better tests that cover the same thing. If you have a test that does not contribute coverage compared to all of the other tests, like all it covers are lines that other tests are covering, and if this test is a big test, for example, maybe you need to drop it, or maybe you need to think about it, okay? So the other thing that's very important for me is when I read this code, I see something that's strange. I don't understand why is this line like this, why is this conditional, doesn't seem correct, doesn't seem complete. And then what I do first, I do a git blame, say when was this last changed, and then I read the comments for that commit message. Okay, who did it and why? Typically the comments have a reference to the bug report that they fixed. I go read the bug report. And then I start to put together a picture of why this strange code is there. And it's strange perhaps because I can't really imagine the situation where it's used, and maybe that's why there was a bug, because people couldn't imagine why that's needed. But if I want to go beyond that, I say, I want more concrete. I want to execute this statement in my debugger. Well, I have 700 tests. Which one do I run? So you right-click on the method, you find the test, put the breakpoint there, and run this test. You can do this all with a few clicks of the mouse in an IDE. And then immediately you're brought to that line in the debugger in a very concrete situation where you can examine what happens. Okay? The other use of this is I'm in the middle of a method, half of it is red, it's not covered. I want to write a new test. Well, the easiest way to write a new test is to adapt an existing test. So I find a test that comes nearby, I find the closest line that's covered, put a breakpoint there, and see which tests come here, and go look at the test. So probably a very similar test would come there and then take a slightly different path to where I want to take it. Okay? So that's actually very, very powerful. You could achieve the same if you just put a breakpoint and run all the tests. It may take, a minute. It'll stop eventually there, and then you can understand the test and understand how to change it.
What tool is this right here? The test contribution charts.
This is the same Clover tool that we saw before. This is from Atlassian.
So Clover's like a test coverage.
It's a test coverage tool for Atlassian. Yes, it's really for Java. I do not know if PyCharm has this. I don't think the coverage tool in PyCharm has this feature. But I wanted you to. So what I do really, I put a breakpoint there and run my entire test suite, and then see which tests stop there. Okay. Let's. Any questions? I want to spend 5 more minutes to tell you about how not to use code coverage. But perhaps by now you'll have the idea that it's a useful quantitative metric, but like any metric that tries to be very precise, like 95.7%, a very precise description of something so complex as to how many cases I have covered in my code, it's a precision that's kind of gives you a false sense of precision. So here's one example. Consider that you wrote this code. This is your production code that you're trying to test. You perform some operation, you get some status code, and if status equals fatal error, then you do something, some error recovery or error reporting. Okay? And you run your tests, you collect test coverage, and test coverage tells you that this conditional is not fully covered, this line is not covered at all. Okay? Well, you know what you need to do. if you want to cover it. You add another test case that somehow induces this the perform operation function to return the fatal error, and then the test will take this branch and this will get executed, and you verify that the recovery works. But are you done? Okay. What if you forgot to check for other errors that may be found by this function? And this is very common in languages or projects that don't use exception handling. Projects that rely on this kind of code pattern where the programmer has to check the error cases they care about. Okay? What if this perform operation returns another error, even more fatal error, let's say, and you forgot to write the code for it? Code coverage will never tell you about code you forgot to write. It's a bug, but it's not a bug you can do anything about because it kind of only looks at the code you wrote and find out how much of it you tested. Cannot do anything about the code you forgot to write. Okay, this is a very significant problem. So code coverage has value, and it's good that it's a numerical metric, but don't put too much weight on the particular number. Okay, because 95% code coverage can mean different things. It can mean that there's 5% of your files that are not even running. That's bad. But it may mean that there's 5% of code, some of which is really not reachable, or some of which is very hard to exercise in tests. But if you look at it, it's actually fairly simple code. So there's probably not a lot of bugs that are lurking in there. At the same time, having 100% coverage doesn't mean that you've covered it all. There's a lot more about code than can be captured in a simple metric that counts statements, right? Because you can have actually fairly small code that's very complex behavior. So for example, you could have a bug that only kicks in when a loop has executed, 1,025 times. And up to 1,024, it works perfectly fine. Okay? So none of the coverage measures I showed you would actually point that out because it shows, well, everything's covered. Branches, statements covered. So not only is 100% really not enough, but it's also very, very hard to achieve. Some big projects that have written without tests from the beginning, they're struggling to get over 80%. Right? Especially since they start with the mentality that we'll write the test when we're done. Well, guess what? They are done a little bit too late, so they have to ship. So now they feel this kind of pressure that they have to write tests, but the code is done, or so they think, and you want to ship it. So they'll probably not get to 100%. Okay, so do use test coverage, and we want you to use test coverage and report test coverage in your projects, but use it intelligently. Use it to point. Don't just report the number. Look at where is the coverage lacking, and is that code deserving a test? Perhaps yes, perhaps not. Okay, and remember, code coverage will never complain about code that you forgot to write. In day one of your project where it does nothing, you can cover it 100% very easily. Okay, it doesn't mean it's correct. So let me stop here.